Okay, so today we're going to talk about 3.5, the implicit differentiation. And so last Tuesday when we met, we talked about uh, the chain rule, right? And the chain rule was we have functions that it's got an inside function with an outside function, so we have to take the derivative and work through the problem, correct? With the implicit is something very, very weird. Now we're going to have variables that we don't know what the variable, how it's broken down. And so we're going to assume that that variable is a substitution of the variable we're deriving by. Okay? And I'll explain that to you guys right now. Okay, so this first example that we have here is xy equals 1, right? And one of the things that we can do with this problem is, since I want to take the derivative with respect to x, I'm going to solve this for y. So I'm going to take this thing and I'm going to go, okay, y is equal to 1 over x, correct? Okay, so when I go to take the derivative, I'm going to get dy dx, right, because we're deriving with respect to x, is going to be the quotient rule, right? And the quotient rule tells us the derivative of the top, so that should be 0 times x, minus the top times the derivative of the bottom, which is 1, all over the denominator squared. Agreed? You guys remember that? Okay, cool. So then when we clean this up, we should get dy dx is going to equal negative 1 over x squared. Agreed? Okay. So now we're going to attack this problem in a very different way. So again, same problem, xy is equal to 1, but now we're going to pretend that we couldn't solve this thing for y. We couldn't isolate for a variable, okay? So what we're going to do is we're going to take the derivative with respect to x of both sides. Agreed? Okay, so now on one side we have a product, correct? So if we know the product, we're going to take the derivative of the first, and the first is x in this case, correct? So the derivative of the first is going to be 1 times y. Agreed? Plus the first times the derivative of the second. But we're taking the derivative of the second with respect to x. We don't know what it is. We don't know if y is some function in terms of x. So we're just going to call it dy dx. Or if you used prime symbols, you would have just gone y prime. Okay? Is equal to, what's the derivative of 1? Should be 0. Should be 0. So then from here, I'm going to get y plus x dy dx is equal to 0. I'm going to move the y to the other side, so I'm going to get x dy dx is equal to a negative y. Agreed? Wouldn't it be 1? What would it be 1?
Oh, the derivative of 1? Like, how would you get 0?
Okay, so we have to go back to what's the derivative of a constant?
Oh, 0.
Yeah,
Okay,
because you can think of y is equal to 1 is a horizontal line. Slope of a horizontal line is 0, right?
Yeah, right.
Okay, cool. Okay, so then from here, I'm going to divide by x. So I'm going to get dy dx is equal to a negative y over x, right? Okay, that's the same answer as the other side. You don't believe me, do you? Want me to show you? Okay, I'm going to just do a little manipulation here, just so you guys can see that it in fact is the same thing. From here, I know that y is equal to 1 over x, right? Now remember, the whole point to doing implicit is I can't solve for one of the variables. So I had to demonstrate it with an example that I can solve so you can see that it in fact is the same. So instead of negative y, I'm going to change that to a negative 1 over x over x. You guys agree? And when I divide by x, I multiply by the reciprocal of that, which is going to give me a negative 1 over x squared. It's the exact same answer. Any questions?
Yes, question. So if you wrote the answer as negative y over x, would that still be acceptable?
So when we do implicit, you're going to have variables that are both. I'll do it in just a second so you can see a more complicated problem. But yes, you'll have answers that have x and y in them.
All right, okay.
It'll be all right, I promise. It'll be all right. Gerardo says, is that A minus B? Where? Oh, you're muted. Unmute yourself.
Where it says x, y would give x equals minus b. The second line, second to the last line.
Here?
Yeah, is that a minus b?
Oh, my writing is terrible. I apologize. So this
sorry,
is
so it's a minus y.
negative y. Yeah.
Oh, okay, thank you.
Yeah. Okay, do you guys want me to show you how this works in a crazy math problem?
Yes.
Okay, so this example that we have here, and I'll erase that line, we don't need that. Is it possible, and I'll just write it down real quick so you guys can see, is it possible for me to solve this for just y? The answer is yes, but I'm sorry, the answer is no, because what ends up happening and complicates things is I have y here and I have y here. Now, if this would have been an x, I could have solved for y. But because I have y in one piece and y inside of a sine, it's impossible for me to be able to solve for the variable y. Correct? Whenever you see this in these problems, this is when you need to, that's when you need to do the implicit differentiation. If you cannot solve for a variable, you will need to implicitly differentiate. Is that clear? All right, I'm about to go cray. Ready? So here we go. Okay, so from here, when I take the derivative of this piece right here, what's the derivative of that going to be? 10y, perfect. 10y. Plus, what is the derivative of sine of y? It's awesome. So many of you guys, I love it. You're going cosine of y, Montiel. Problem is, you missed something. You missed the chain rule. Cosine is the outside function. Y is the inside function. Hence, we need to take the derivative of y. So that becomes dy dx, or if you want, you can write y prime. That is the chain rule now being applied implicitly. Make sense? Then on the other side, what am I going to get? I should get 2x. Now, I made a mistake. It's funny. What did I forget here?
The dy dx.
Oh, Carol pointed it out. There should be a dy dx there. Why? Because I did the outside function, I did the square, but I never took the derivative of the y. So this one here should be 10y dy dx. Does that make sense? If not, I'll explain it to you so you can see.
Yes, please explain.
All right, no worries. So check this out. So let's say that the outside piece was the square. The inside piece is the y, right? Our constant is just a constant, okay? So when I do the outside piece, that's the square. I take the derivative of the square, right? So I'm going to get 2 times 5. Then I have my y, right? And then that's going to go to the first power, correct? But have I taken the derivative of the inside function, the y? No, I need to now, so I multiply by dy dx.
Where does the square go, though?
So it's the power rule. So if we go back to just power rule, remember the power rule told us, if I take the power
so
rule,
you're like doing it twice.
so that's the power rule, right? That brought the 2 down. But then what happens in this, when we really do the chain rule to this, and I'll do this so you can see, we take it for granted. That's a green x. We should have the derivative of x with respect to x, right? Or really the way I should say it is I should go that derivative, right? What is the derivative of x?
1.
1. So that's why we just say n times x to the n minus 1, because the derivative of x is just 1. But when we have a variable in there that's called y, we don't know what y is, so we just call it dy dx. So, case in point, let me show you. So you guys can truly see how complicated this gets. Okay? Oh, I shouldn't have erased that. But okay. Let me tell you that y is equal to x squared, let's say. So I'm just substituting y for x squared, right? So when I do the power rule, I'm going to get 2 times that 5 times the y, right? With the, and I'll even write the power rule fully so you can see it, 2 minus 1. But what happens here is, if y is something in terms of x, don't I have to take the derivative of the y? Right? So this means, this is the implicit piece, it's dy dx. Okay? Now, watch this. I'm going to make the problem identical. So that was the substitution that I did for this problem. So in this problem, we get 10y dy dx. Over here, I'm saying, all right, the problem is 10y squared. But when I substitute, don't I get 10x to the 4th? So now let's take the derivative. What's that going to be? Isn't that 20x to the 3rd? Okay, watch this. Because I want you guys to see it, make the connection. What would the derivative of this piece be right here? What is this? 2x?
2x.
2x? Okay, cool. So we're saying, and I'll do it in a different color because I want you guys to be able to see this. We're saying this would be 2x, correct? The dy dx?
Mhm.
What's the y equal to? It's right there.
10y
It's right here.
equal to, x squared.
X squared.
Should be 2x.
And then there should be a 10. What do those things multiply out to be? Isn't that 20x cubed? Do you see what's happening here? Something that you guys have probably never really thought about. Sometimes we use variables, we call them dummy variables, to represent other functions. So in this case, I said, hey, let me let y be y or x squared. But when I take the derivative in terms of x, I need to remember that y is something in terms of x. So I must differentiate it implicitly. Does that make sense? So really the implicit, what it's telling us is we've done some sort of silly substitution for the variable we're deriving for. Okay? I know it's complicated. Let me finish this problem so you guys can see. So then from here, I need to get dy dx by itself, right? So I'm going to get dy dx 10y plus cosine of y is equal to 2x. So then dy dx is equal to 2x over 10y plus cosine of y, and that is my answer. My answer is going to have both x and y's in it. Because this y variable that I have in here is something that's really a substitution of a function in terms of x. Make sense? Do you
So
see?
the reason, because like you finished it and it was like the 2x over 10y plus cosine of y, you didn't, because it was like derivative, but you don't take the derivative again, you just kind of express it into like one piece.
You want to isolate for the dy dx.
Okay.
Because the dy dx is the derivative, correct?
Mm-hmm.
So what is the derivative equal to? It's equal to 2x over the quantity 10y plus cosine.
Okay. So you wouldn't do, you wouldn't take the derivative itself of it because of the y.
Oh, we could do another derivative of it. We will eventually. They get really complicated. But baby steps.
Okay.
Right? First we gotta be able to crawl. We'll get there. We'll get there. But do you guys understand with the example that I showed how it becomes a substitution for something in terms of x? Did this help clarify it for you? Or did it just confuse you more?
Both.
A little bit of both? Yeah. No, for sure. See here, the thing here is this thing, you have to think of it as this represents something in terms of x. And since it represents something in terms of x, when I take the derivative, there's the power rule. It stays the same because we're doing the outside function. But then the chain rule piece to this tells me I need to take the derivative of that. But if y was just y, it didn't have anything to do with x, this would become 0, correct? But since I'm telling you it's doing something in terms of, it's a substitution in terms of the function with x, we need to implicitly differentiate. You want me to do another example? Okay.
Yes, please.
All right. So now in this example, we're doing something pretty interesting. I'm actually giving you a point. So because I give you a point, I'm giving you an x and a y. We're going to actually be able to find what the specific derivative value is of this problem. Okay? Because it's saying find the slope of the tangent line at this specific point. No problem. So let's look at this. So remember, everything that's in terms of y in this problem is something that we can write in terms of an x function. Now, looking at this thing first off, can I solve it for y alone?
No.
No. As soon as we get that, we're like, ah, dang. We must do the implicit. Okay? And now when we attack the implicit, it's really 4 basic derivatives, right? So what's the derivative of the first piece? The 7y to the 4th.
28y third.
28y to the 3rd. We're missing something.
dx, dy, d something, those, yeah.
It's dy over dx, right? The bottom number, the bottom variable, the x in the bottom, is what we're taking the derivative with respect to. So basically what it's telling me that this bottom letter right here is saying I'm trying to find out what the derivative is for x's. Okay? Okay, what about the next one? It's a product, correct? This here ends up being a product, so I have to take the derivative of the first. So that's going to give me 3x squared. And really, I could do the chain rule to that, right? I could take the derivative of the x. What would the derivative of the x be? What's the derivative of x? It's 1.
1.
Right? It's 1. So we never write it because we know, right? The derivative of that is 1. Okay, times y, plus, because we're doing the product rule, the first, x cubed, but what's the derivative of y?
Y prime.
Y prime or dy dx. The next term, now we're dealing with the x. What's the derivative of the x? It's got a 1. Yes, I'll write it out for you. And then what is the derivative of 4?
0.
Perfect, it's 0. It's 0. Okay, product rule. If I have f times g and I go prime, I'm going to go f prime times g plus f times g prime. So here, the derivative first was a 3x squared times the y. Then the first times the derivative of the second, and that's dy dx. We okay? Okay. Now what we want to do is we want to isolate to get dy dx on one side. So what I'm going to do is I'm going to go, all right, 28y to the third plus x cubed is equal to times the quantity dy dx, right? I factored out dy dx out of both of those. The other two need to go to the other side, so I'm going to get a minus 1 minus 3x squared y. Are we okay with that? Right? This has no dy dx, this has no dy dx, so when it goes to the other side, it has to change signs. Do you guys see why I wanted to teach you this and not record it? I'm lost. How come? All right, where are you lost, Carol?
How come it's not like d and then over dx? It's like dx over. It's dy over.
Why is it dy over dx? Okay, the reason it's that is what's the variable that's being represented, that's being derived with respect to x?
Y.
It's y. It's y. So check this out. If I had done something like z and was taking the derivative with respect to x, that would become dz dx. So whatever the variable of the unknown is, that's the thing that goes next to the numerator d. Does that make sense?
Thank you so much. Now that blew my mind, because I was doing the homework and there was like find the dA and then over dx, and I was like, how come they're changing that part all the time?
Yeah, it's because whatever the variable is that you're doing it in. Does that make sense? All right, cool. It's good to ask, right? Okay. So then from here I have to divide by what's with dy dx. So I'm going to get a negative 1 minus 3x squared y over 28y cubed plus x cubed, right? That's the derivative. But this problem is saying find the slope, right? So since it's saying find the slope, I have to evaluate this at 4, 0. Okay, where 4 is x, and we have our 0. So I'm going to get, all right, the slope of this thing is going to be negative 1 minus 3 times 4 squared times 0 over 28 times 0 cubed plus 4 cubed. And that's going to give me a negative 1 over 64. And that is the slope of the tangent line of this implicit crazy thing. You guys feel like you're starting to get it a little bit?
Yeah, I feel a little better.
All right, good. Okay, let me give you the derivatives to the arcs or the inverse trig functions. So you have them. It's another tool that you guys should have. And then I'll make up a problem that you guys can try to do using the implicit, okay? All right, so here are these derivatives for you. These you should write down, have them on a table, have them under reference. They will save you. The derivative of arc sine is 1 over the root of the quantity 1 minus x squared. Cosine is just going to be the negative of that exact same thing. Tangent is going to be 1 plus x squared. It's funny that I wrote it this way because this is just the negative of that one. And then the secant and cosecant. Secant is positive, and cosecant is negative. So all the cos again will be the negative ones. All right, and those are just for you to work on and memorize. Let me create a problem for you guys to try, okay? I want to give you guys an opportunity and see how we go. All right, so let's say, do you want it hard or easy?
Let's start easy.
Okay, cool. I'm just going to make it up off the top of my head. All right, try that. You guys ready?
Yeah, I hope so. I think our answer's correct.
Okay. So let's look at this. So this first piece here, this is a product, right? So that means we're going to have to use the product rule. So I'm going to write it down so it looks like the product rule to you guys, okay? So I'm going to go, okay, this x cubed thing has got to be primed times y to the 1/2 plus x cubed y to the 1/2 has to be primed, correct? Then the derivative of tangent should be secant squared y, but then I need my dy dx because of the chain rule, right? And then the derivative of x is 1. Are we in agreement so far? Okay. By power rule, I'm going to get 3x squared y to the 1/2 power plus x cubed times 1/2 y to the negative 1/2 power dy dx plus secant squared y dy dx is equal to 1. Does everyone follow my work so far? Any questions? You good? Okay. So I have the 3x squared y to the 1/2 power has nothing to do with dy dx. So I'm going to move that to the other side. Okay? So I'm going to end up with 1/2 x cubed. Oops, I'm actually going to clean this up so it looks pretty because I'm all about pretty. Make it really pretty. Let's go x cubed over 2y to the 1/2 plus secant squared y in agreement? So then when I go dy dx, I'm going to have 1 minus 3x squared y to the 1/2 over x cubed 2y to the 1/2 power plus secant squared y. Do you see why I want you guys to do homework on this? Any questions? Are you guys just trying to breathe? You guys feel okay? You want me to give you another one?
Sure.
All right, let me give you another one. I'll try to make it a little bit simpler.
Surprisingly got that one correct.
Nice, good job. This one's a little bit tough. You guys ready for me? It's all right, Ray. I saw that, dude. It's cool. All right, so check this out. On this first one that we have, this first piece, the sine xy, we clearly see that this is a chain rule problem, correct? That also within the chain has a product rule within it, right? So what is the derivative of sine? That one we can all do. We're all so happy to say, okay, cosine of xy, right? But that cosine of xy needs to be multiplied with this product that we have. So what is the derivative of x? And what I'm talking about is now I'm talking about this piece right here, right? So the derivative of x is 1 times y plus x times dy dx. Is everyone okay with that? Okay, Ray, where are you spun on this?
Why is it x times dy over dx?
So why is this here?
Yes.
Okay, I can write it another way that may help you. Instead of writing it as dy dx, I can write it as y prime if you'd like. That's just saying that I'm taking the derivative of the y. So by the product rule, remember, the derivative of the first is 1 times the second plus the first times the derivative of the second.
Oh, okay.
Does that make sense from this?
Yeah. So, like, that 1 is actually x to
the derivative of x. That's right.
Okay.
You follow?
Yeah.
Okay. And then that y prime is just the derivative with the derivative of y with respect to x. Okay?
Okay. Mm-hmm.
So there's the first piece. Then plus 2y, but then we need the y prime, right? Because of the chain rule. Do you agree?
Sure. Yeah.
You do?
Yeah, yeah.
All right. And then we already did this one. It's right here, right? This is just this piece right here repeated. Do you agree?
Yeah.
So I'm going to get 1 times y plus x times y prime.
Okay.
Now, for clarity's sake, this is what I'm going to go try to get. This one I have to get, and this one I have to get. I want to put those all in the same place together, right? Because I want to be able to factor out a y prime. We okay? So that means I have to distribute. So I'm going to go, okay, y cosine of xy plus xy prime cosine of xy plus 2y y prime is equal to y plus xy prime. Okay, so what I'm going to do is I'm going to move to this side, y minus y cosine xy. And over here I'm going to get x cosine of xy plus 2y minus x y prime. Do you follow what I did? Okay. This has nothing to do with the y prime, correct? So when I move that to the other side, I have to subtract it. Hence, I get this. Okay? So I'm getting y minus this piece that I moved. This has to get moved to this side, so it's got to become minus, right? So minus x y prime. Isn't this x times y prime? And it's a minus. All I did was I factored out the y prime. So look here. X cosine xy y prime. There's x cosine xy. still multiplied by y prime. 2y, y prime. Here's 2y, still multiplied by y prime. Do you follow? Or do you want me to write that step in between? I don't mind.
I think I get it. To get the y cosine xy, you factored the 1y plus x plus y derivative.
Are you talking about from here to here?
Yeah.
Yeah. So this multiplied by this thing, because it's a bracket, you see?
Yeah.
So cosine xy times 1 times y, that's y, right? So y cosine xy is this piece. And then here, xy prime times that gives me xy prime cosine xy.
Okay. Okay, then now I get it.
Yeah, it's just algebra with a word, like letters and stuff, right?
Not just algebra.
It is just algebra, but it's a sketchy algebra, right? So then the next thing that I need to do is I got to get y prime. Oops, I got to get y prime alone, and so I'm going to get y minus y cosine xy over x cosine xy plus 2y minus x, and that's my answer.
Professor, I have a question.
Sure.
So for every problem that we were doing, it's with respect to y, right?
So it's with respect to x, because remember...
I'm sorry, x.
Yeah,
yes.
It's the bottom one that we're doing it. So that's a great question. If I had done something like dx dy, like this, that's a totally different derivative.
So we would do it...
You would take all the derivatives of the y's instead. Would you like me to show you?
Okay, because it would be just like the opposite. It would
Yeah.
just be we would take the derivative of y, and that would equal to 1 instead of...
So I'll do one where you can see both, okay? So let's just say I had x squared plus y cubed, right? And I'll do it implicitly just so you can see. If I go dy dx, this means I'm taking the derivative with respect to x, right? So this would become 2x plus 3y squared dy dx, correct? Well, let me make it equal to something too, just so we can do it. So then that would become a negative 2x divided by 3y squared is my dy dx, right?
Yes.
You follow that one? Okay, so now let's do it with respect to y. So if I do it with respect to y, same problem. I'm going to get, all right, 0 is equal to 2x dx dy plus 3y squared. Do you see where the implicit comes into play? It's in the variable that we don't know.
Yes.
So this ends up being that. See the difference?
Yeah.
So depending on what variable we're taking the derivative with respect to will impact the answer. Now, to ease your nerves, I'm going to always ask for dy dx.
Oh, I know. I wasn't sure if the homework I asked which specific.
Yeah. So I think all the homework is going to be in terms of dy dx also.
Oh, okay. Thank you.
Yeah. Because one thing you have to remember is eventually when we get to three-dimensional drawings, we may be dealing in the YZ plane. So taking derivative with respect to x is nonsense, right? Okay, can we go on to the next section? All right, let's do the next one. All right, this is 3.6, taking the derivative of logs. All right, It's not too bad. There's a couple of things I want you guys to know, and so I'm going to give you some basic information. The derivative of log base A is going to be 1 over x ln of A. The derivative of ln of x, it's one you guys will use a lot, you'll memorize this, is 1 over x. And then when we're doing it with an unknown variable, it's again the chain rule, it's 1 over u, but then it'll be du dx. That's the implicit piece, right? Like if I would have made that ln of y, it would have been 1 over y dy dx, right? I just used a different variable. But that is the implicit. Understood? You can say no. You don't, okay. So check this out. So if I had, so I don't confuse you with variables. If I had this with respect to x, right, and I go ln of y, okay? The ln piece, we know the derivative of that is going to be 1 over whatever the variable is, right? So that gives me that 1 over y, right? But since we're doing it for a variable we don't know, x, I have to take the derivative of the inside piece. So the outside function is ln, the log function. The inside function is y, and I have to do the chain rule to it. But since it's a variable I don't know, we call it implicit. Right? Does that help, Ray? All right, cool. Okay. So, what's the thing I'm going to do first? Oh, the first one? That's x ln of a, David. Does that make sense? Okay, he didn't reply. All right, so, yeah, okay, cool. Okay, so this first example I'm going to do for you is this. So here's the way you want to look at it. This, if we just call that some variable we don't know, right? We'll call it gold. From the rule of ln of u, don't I get 1 over whatever that gold thing is? Right? And the gold thing is x squared plus 1. But then we have to take the derivative of the gold thing. So what is the derivative of the gold thing? That's right, it should be 2x. So that tells me that the answer is 2x over x squared plus 1. It's the chain rule. The outside function ln, the inside function x squared plus 1. This will come up a lot. Okay? All right, I'm about to give you headaches. You guys ready for some headaches? Okay, can I move this up? All right. These are the steps that you're going to use to be able to solve these problems that I'm about to do. Okay, so we could have done this problem by the quotient rule with a product rule, and it would have been ugly, right? Right? You guys see how ugly this thing could be? just a reminder, can we do the log? I think that's log. Yes, to both sides. Yes, you can do it to both sides. So I'll show all that. So with these problems, what you're going to do is instead of trying to do the product rule and all this stuff, and then you get lost in a bunch of algebra, we're going to take the natural log of both sides, and then we're going to differentiate implicitly, and then try to get our dy dx out of it. Okay? So, are you guys ready? So here we go. I'm going to go natural log of y is equal to the natural log of x squared, the cube root of 7x minus 14 all over 1 plus x squared to the 4th power. And then, you guys all know your log rules, right? Here they come. So the natural log, what I'm going to end up getting is the natural log of x squared plus the natural log of the cube root of 7x minus 14 minus the natural log of 1 plus x squared to the 4th power. Do you remember that? Products add, division subtracts. Okay? Exponents become coefficients, right? So ln of y is equal to 2 ln of x plus 1/3 ln of 7x minus 14 minus 4 ln of 1 plus x squared. Do you agree? Any questions so far? Are you all falling in love with math? Or are you all thinking about going to some other major? No, this thing's cool, man. Okay. So now I'm going to take the derivative of everything. So the derivative of ln of y is going to be 1 over y dy dx, correct? This is going to be 2 over x because ln of x becomes 1 over x, right? Plus 1/3 times 1 over 7x minus 14, but then I have to take the derivative inside, so I have to multiply by 7. Right? By the chain rule. Minus 4 times 1 over 1 plus x squared times 2x. In fact, just to be consistent, I'll go 2 times 1 over, just so you guys can see it all. Did I break that down enough for you all? Okay. So I'm going to get 1 over y dy dx is equal to 2 over x plus, I'm going to do a little manipulation here. I'm going to get 1 over 3 times x minus 2 minus 8x over 1 plus x squared. Does everyone see what I did there? I factored out the 7 in the denominator. You see it? So that's why I got x minus 2. So it would cancel the other 7. Okay. You can unmute yourself, dude. It's cool. It's actually beneficial for when people watch the recordings because the chat's not there. Okay. So then from here, I need dy dx to be alone. So I'm going to get y times 2 over x minus 1 over 3x minus 2 minus 8x over 1 plus x squared. But guess what? I know what y is. Don't I? So dy dx will only be in terms of x if I substitute. So I'm going to get x squared, the cube root of 7x minus 14 over 1 plus x squared to the 4th times 2 over x minus 1 over 3 times x minus 2 minus 8x over 1 plus x squared. Merry Christmas.
I have a question.
Please.
So, from the third one from the bottom, it goes from there, and the sign's changed. Why?
Oh, because I'm silly.
Damn. Okay, cool.
Thank you.
No problem. So 1 over y times dy over dx, you're multiplying y times.
Correct. I'm multiplying both sides by y. Because the goal is to get the derivative by itself, right? The dy dx by itself. So that means I have to multiply both sides by y. But then in the...
Oh. Okay, got it.
Right?
Cool.
And then we have to remember that at the beginning of the problem, y is equal to this thing. So since I want everything in terms of x, I'm going to substitute the original problem back in.
Okay, it doesn't matter that it's natural log of y?
The original problem was just y is equal to.
Duh. Okay, cool.
Does that make sense?
Yep, totally. Christmas. Austin, thank you.
Yeah. Look, as long as it makes the connection for you, that's the big thing, right? So...
whenever you have a natural log, you just have to put whatever's inside the parentheses into inverse, right?
whenever you have the natural log...
Like you see how for go about 3 steps up where you still have natural logs in the problem?
Here?
You have to put like for the first one, ln of x, you have to convert it into 1 over x, right?
Correct.
Everything into the...
Because of this.
Okay.
Does that make sense?
Yeah. Can I see that thing up there one more time, please?
Oh yeah, no problem.
Okay, that's fine, thank you.
It's these notes are up on Canvas too, just so you guys know. And I have the filled in notes all the way, not 3.6, not up to 3.6, but I'll put those up right after this class. But they're all up on Canvas for you guys, so you can reference them. Does anyone need to copy this, or can I go on to the next problem?
Could you just explain, I know you said something, but I still don't really get it, of just where the 7 went? You said you factored it out?
Oh, here. Right here?
Yeah.
Sure. So I have 7 over 7x minus 14. So I'm going to go 7 over 7x minus 2. So that gives me this right here.
And then you multiply the 3 over. Cool.
Does that make sense?
Yeah, yeah.
All right.
Professor, how soon is the video going to be available?
Oh, so I'll post it up right after this. I stop recording. I'll start going through the process. It'll probably take about 30 minutes to an hour. It's just,
okay.
It's silly, but it takes some time.
Yeah.
Yeah, the processing. But it'll be up in about an hour after class is done. Okay? All right, can I do the next problem? All right, here we go. So this problem here, what ends up happening is you probably can't see it very well, so I'm going to write it in a way that you can see it. This problem isn't this. It's this. Okay? I know it looks like the first one. It's not. Okay? That's an exponent. It's just the program I use, map type, makes it looks like it's almost like it's a product. So I don't want you to mess that up. So I'll just rewrite it. It's y is equal to x to the cube root of x. Okay? So when we have something like this where we have an exponent that has the variable in it, we want to use this method with it also. So what I'm going to do is I'm going to take ln to both sides. So I'm going to get ln of y is equal to ln of x cube root of x. Okay? Then I'm going to use the rules. Before I try to take the derivative, I want to do the rules, right? Because if you don't do the rules, it'll mess you up in terms of being able to do these problems. Okay? That's important. Use the rules to bring the exponents out front, and then you do the derivatives. Okay, so then this one is going to be 1 over y dy dx. Everyone agree with that?
Sure.
Okay. This one is going to be 1/3 x to the negative 2/3 ln of y plus the cube root of x times 1 over x. Does everyone agree with that? You can say no.
I'm confused on doing the cube root into a fraction.
Okay, so all about that Christmas life, right? So think of it like this. It's x to the 1/3 ln of x, right? So when I do the power rule to the first, I'm going to get the 1/3 out front, x to the 1/3 minus 1 ln of x.
Got it.
Plus x to the 1/3 times 1 over x.
Professor, for that last step, you did the product rule, correct?
Correct. That is the product rule, and that's why I put it. That's why I colored them, F and G, right? So you can see that it's the product rule. So then that gives me that 1/3 x to the negative 2/3 power ln of x, and then we could clean that up, right? We can say that that is x to the negative 2/3 power. Do you see that?
No.
No? Okay, so think of it like this. It's okay. No, it's cool, dude. Don't trip. There's no judgment. This thing right here, isn't that the same as writing x to the 1/3 over x? And isn't that x to the 1/3 over x to the 3 over 3? Which gives me 1 over x to the 3 over 3 minus 1 over 3. Which then gives me 1 over x to the 2/3 or x to the negative 2/3.
Okay. Interesting.
Yeah, it's algebra, man. It's algebra. Okay. So 1 over y dy dx is going to be ln of x over 3x to the 2/3 plus 1 over x to the 2/3. Then dy dx is going to be y times ln of x over 3 times x to the 2/3 plus 1 over x to the 2/3. That's a terrible 2/3. And then what's y equal to?
X.
Christmas. How are you feeling?
Study.
What's that?
They have to study a lot with it.
Yeah, this is going to take some time. I know. It's absorbing, right?
Yeah.
So, one thing that is cool. So on Thursday, if you guys are open, I have office hours from 8 to 10 or 8 to 9:30. Hop on, and if you don't have a class, and I'll do homework problems with you guys.
Right.
Okay? All right. Giving you guys a chance to copy this down before I go to the next one. You guys ready for me? All right, let's see. So again, we notice there's a variable in the exponent, so we're going to use the same trick. So I'm going to go ln of y is equal to ln of x cosine of x. Now before I take the derivative, I need to do this. And now I see there's a product there, correct? So when I do the derivative implicitly, I get this. The derivative of cosine is a negative sine of x, ln of x, plus cosine of x times 1 over x. Are we okay with that? You all right? Make sense? Again, just so you guys can see, it's a product, right? It's a product. Okay. I'll get dy dx is equal to y times a negative sine of x ln of x plus cosine of x over x. And then we know what y is again. So we're going to get dy dx is equal to x cosine of x and that's our answer. So when do we use this ln piece? When do we use this ln trick? When you have a variable that you're deriving for in the exponent. Would you guys like to try one and then I'll do it?
Yes.
No. I'll make it very similar to this one, okay? How about I go y is equal to cosine of 5x to the x. It's funny, a bunch of you I'm noticing were former students of mine for all kinds of classes. It's kind of cool. You guys must be gluttons for punishment, wanting to take me more than once. All right, shall I start this? That's nice, thank you. You guys want to see me do it?
That's good.
Okay. So again, the giveaway for this problem is this right here, right? This tells us that we have to do that ln trick. So then I'm going to go the natural log of y, and I'm going to go, do you guys want me to drop it or do you want me to just show it? You want me to show all the steps?
Show it, please.
Let me know.
Okay, I'll show it all. Okay, then the next step, and it's always this way, before you can take the derivative, you must apply the log rules. Because if not, you're going to get confused on what to do. So you saw how the exponent came out front as a coefficient. Now at this point, I can take the derivative. So I'm going to get 1 over y dy dx. And then this is a product again, right? But this green one now is kind of ugly, right? Because it's going to have a chain rule in it. That's okay. The derivative of x is 1 times ln of cosine of 5x plus x. The ln piece is going to make it 1 over cosine of 5x, correct? But then what is the derivative of cosine? Isn't that negative sine of 5x? And then what is the derivative of the 5x? It's 5. Is there any questions on that? It's okay if you do.
I'm just trying to process where, like, x plus ln, that's like 1 over cosine 5x is supposed to be ln cosine 5x, right?
This right here is the ln of cosine 5x
Okay.
derivative, right? That's the ln derivative. This one is the cosine derivative, and then this one is the 5x derivative. So it's ln, then cosine, then 5x.
I see, says the blind man. Okay, cool. Thank you.
Does that make sense?
Yeah.
Yeah. Here, I'll try to show you. So you think of it as ln, then cosine, right? And then the 5x.
So pretty much you have to take the derivative of everything, right?
Correct. It's the chain rule. So it's the outermost function, then the inner function, and the innermost function.
Yeah, okay. So as long as you don't leave anything unaccounted for, you should be fine, right?
Correct. So yeah, I can explain that. I can explain that, Carol. So check this out. When we look at this part here, I know ln is a function, correct? So when I take the derivative of that, isn't that going to give me 1 over the other pieces, right? So the other pieces were cosine and then the 5x, right? But then the next piece is the green. So red was the first, then the green, the derivative of the green is negative sine the 5x, and now I got to do the blue, and the derivative of 5x is 5. Does that make sense with the color? So
I have a question.
Yes, please.
Oh, sorry. I have a question. So if it was, instead of 5x, if it was just x, then you would still have to take the derivative of x, correct?
Yeah, but it's 1, so we just take
it. But it would just be 1.
Yeah, we take it for granted. Yeah.
Okay. Yeah.
So basically, just so you get this, like, and I've said this before, but I want to make this clear. If I go to the derivative of x squared, we all just say 2x, right? But really what it is it's 2x times 1.
Got it.
But then when we multiply, it just becomes 2x, right?
Because you're getting the derivative of the exponent and x?
Yeah, because the outside function is the square. The inside piece is the x.
I get it now.
Does that make sense?
I'm angry at how long it took me to get that.
No,
Okay.
no, it's cool, dude. Like, my job is to make your mind open up to this stuff so you get it. And the only way I can do that is by you asking questions and me clarifying. So, however long it takes, it's my job to get it clear to you. So don't trip. It's good. You got it, right?
Yeah.
Well, there it is.
Thank you.
Okay. So then from here, I'm going to clean this up just because I'm a bit of a weirdo. All right, I'll just do it. Ooh, and that should be a minus. Do you see how I did that? Five times x is going to be the 5x. The minus sign changes it to a minus. Sine over cosine is tangent. It's okay if you don't see it. It's just to make it cleaner. Okay? Now, dy dx is equal to y times ln of cosine of 5x minus 5x tangent of 5x. And then we know what y is. Y was cosine of 5x to the x times ln of cosine of 5x minus 5x tangent of 5x. Christmas. We okay? Any questions on this?
I'll probably have questions when you start doing
No.
So that's when the questions come up.
Yeah, no, of course. Once you start to do it on your own, you're like, wait, that guy made it look so easy. Right?
Yeah.
But, you know, part of the learning comes from the struggle. So, all right, I'll stop recording here. Hopefully we don't lose stuff, and then I'll answer some homework questions. Okay?
I have a question on number 5.
Okay, so let me stop recording.
Oh, sorry.
If we get booted, come back. I'm hoping we don't.